In this video, we're going to take a look at how to multiply and divide radicals, specifically square roots, and even more specifically, principal square roots. So we're going to use the principal square root sign quite a bit throughout this. So why don't we go ahead and begin with just a real quick review of our vocab. Since that's always a big deal, we'll use these words quite a bit. So we've been working with square roots, and more specifically, we've been working mainly with the principal square root. So remember, we have a symbol to denote the principal square root, and that's this symbol. And generically, this is called a radical sign, because as you're going to see later in math next year, there are more kinds of roots than just square roots. There are cube roots and fourth roots and fifth roots, and we're not going to do any of that this year, but um, this symbol gets used in other situations, not just square roots. So it's got a generic name. It's called a radical sign. And the number that is under it, call that number A, that is called a radical, or I'm sorry, it's called a radicand. Radicand. And then the whole thing is generically called a radical. So this whole thing here, this whole thing is called a radical. So today we're going to talk about how to multiply and divide radicals, but specifically square roots. We're still just doing square roots. And we're really just going to pay attention to the principal square root. So again, let's go ahead and just quickly review some of the properties we've already um, used in the earlier section. So let's do a real quick review. Just so you don't, when you go do the homework, you don't have to flip back through a whole bunch of sets of notes. You should just be able to use this set of notes, make things a little easier for you. So um, let's say you have a principal square root. Let's say you have a principal square root where the radicand is two things being multiplied. We talked about how you can split that up into two separate principal square roots being multiplied. Now, again, A and B can't be negative, so so A and B are non-negative. Because if those were negative, those don't represent real numbers. So we need A and B to not be negative numbers. Now, A or B could be 0, but it's kind of a boring one. Because if A or B is 0, you just have the square root of 0, and the square root of 0 is 0. But still, it could be. Now, we're going to turn that property around today and say, well, what if you have two square roots, two principal square roots being multiplied, and you would rather combine them? So what if it would benefit you to combine them into one principal square root? So basically it's going to just be this exact same property here, but thinking of it the other way, because it's an equal sign. So the left side equals the right side and the right side equals the left side. So it's the exact same property, just we're gonna use it in a slightly different way. And then along with that, earlier we talked about what if you had the principal square root of a fraction or a quotient. You could split it up and do the principal square root of the numerator over the principal square root of the denominator. So again, today we're going to turn that around and say, well, what if you have the quotient of two principal square roots? If you want, if it benefits you, you can write that back as the principal square root of a fraction. Now, of course, for both of these, b can't be 0. because you'd be dividing by 0, and that's never allowed. So for all these properties, A and B need to be positive, and then for the first two properties, even though they're the same property, B can be 0, but for the division one, it cannot, because you'd be dividing by 0. Never, ever, ever. Okay. So as far as traditional notes go, there's not a lot to this. We're basically just going to use those properties that we've already been practicing with. But one of the things we are going to bring up at this point is that any expression with a radical in the denominator is not simplified. So anytime in mathematics you have a radical that's in the denominator of a fraction, that expression is not simplified and therefore can be simplified. So for example, let's say you had like 3 divided by the principal square root of 5. Now that's a perfectly legitimate number. It's an irrational number, but it is a number. It's a real number, but it's not simplified because it has a square root in the denominator. So the reason that's not simplified is if you try to divide by an irrational number, that's a huge pain. You guys have all done long division. Imagine trying to do long division where the denominator is a decimal that never, ever, ever, ever terminates. It never has an end. It's a decimal that just keeps going and going and going. So trying to do that long division, that's a pretty tricky situation. So we don't want to divide by such a number. So this can be simplified, and we're going to talk about how to simplify that today. Another example would be something like 1 divided by the principal square root of 2. That's not simplified. Principal square root of 7 over principal square root of 15. That's not simplified. We have a radical in the denominator. The radical in the numerator is perfectly acceptable. You can't avoid that sometimes. So having a radical in the numerator, not a problem. But if there's a radical in the denominator, then it's not simplified. Another example would be principal square root of 2/3. And you might be thinking, well, wait a minute. I just see one radical. It's got a 2/3 under it. Why is that not simplified? Well, as our property says, the reason this isn't simplified is it's equivalent to this, and that would put a radical in the denominator. So the point here is that anytime you come across a fraction that has a radical in the denominator, that is not simplified. So if you need to simplify it or are asked to simplify it, we're going to show you how to do that. We'll talk about how to do that today. So a little bit of vocab here. Removing a radical from a denominator it has a name. It's called rationalizing the denominator. So anytime you hear somebody refer to, well, you need to rationalize that denominator, or did you rationalize the denominator, or the directions say rationalize the denominator, what they're telling you is you've got radicals in the denominator and you need to remove them from the denominator. So that'll actually be the first thing we practice. So our directions are to simplify. And for our first one, let's simplify 2 over principal square root of 3. So the reason that this is not simplified is we have a radical in the denominator. That is our problem. So this right here is the issue. So we have a radical in the denominator. So the reason this isn't simplified is because of that radical. Otherwise, we'd be good to go. It would be simplified. We'd be done. But since we have a radical in the denominator, we've got to deal with it. We want to get rid of it. Because if I actually needed to get a decimal approximation for this, trying to long divide by that irrational number, principal square root of 3, that would be just a huge undertaking. And if we can avoid that, we would want to avoid that. So how do we get rid of that radical? Well, we're just going to use our knowledge of square roots. So we're going to start with 2 over the principal square root of 3. And we know that from the beginning of the year, and we've used this often, that any number is equal to itself times 1. So if you take any number times 1, it leaves the value of that number unchanged. This is called the multiplicative identity. You can multiply any number by 1 and it leaves its value unchanged. So 2 over the square root of 3 times 1 is still just 2 over the principal square root of 3. So what we're going to do then is we're going to say, well, 1 is equivalent to, use some color here to help you out. This 1 is equivalent to the principal square root of 3 divided by the principal square root of 3. So any number divided by itself, except 0, is equal to 1. So instead of 1, I'm going to replace it with the principal square root of 3 over the principal square root of 3. Now, why did I choose that? Well, because we know from earlier that when you take a principal square root times itself, it removes the radical. The radical sign disappears. So let's see that in action. So we're going to multiply these two fractions together. So we're going to do top times top, and then we're going to do bottom times bottom. And we get 2 times the principal square root of 3 over the principal square root of 3 squared. But we know that the principal square root of 3 squared is just 3. So remember, 3 times 3 is 9, so the principal square root of 9 is just 3. So by multiplying, by taking the original number times the square root of 3 over the square root of 3, we, at the end, ended up with a fraction that had no radical in the denominator. So this number here and this number here are exactly the same number. They would be the same position on the number line. If you have a calculator handy and you type them both into a calculator and hit enter, you will see the exact same decimal approximation because they are the exact same real number. However, the one on the right is simplified. The only difference is the one on the right is simplified. Okay, so what's important here is that this shows that 2 over the principal square root of 3 and 2 principal square root of 3 over 3 are represent the same value. So they represent the exact same value. However, 2 square root of 3 over 3 is simplified. All right, let's try another one. So if we had, let's say we had the principal square root of 1/5. So using our properties, we could say, okay, that's the principal square root of 1 over the principal square root of 5. But we know from earlier that 1 is a perfect square. So 1 is the same thing as 1 squared. 5 is prime, so it's not a perfect square. So the top is just 1. So pretty quickly we can show that the numerator is just positive 1. But that leaves a radical in the denominator. So we're going to multiply we're going to take that number times 1, but instead of using that version of positive 1, we're actually going to multiply by the principal square root of 5 over the principal square root of 5. So we're going to do top times top, and then we'll do bottom times bottom. We're going to get principal square root of 5 over principal square root of 5 squared. The top's not going to simplify because 5 is prime, but the square root of 5 squared is just 5. 5 squared is 25, and the principal square root of 25 is 5. So we end up with this version of our number that is simplified. So again, so principal square root of 1/5 and principal square root of 5 over 5 are represent the same real number. However, principal square root of 5 over 5 is simplified though. That's the difference. So they represent the same number, but principal square root of 5 over 5 is simplified. Let's do one more. These are very repetitive, just the numbers change. Let's say you add 9 principal square root of 3 over the principal square root of 24. Now, one of our properties says that if you have two principal square roots being divided, you can, so this would be 9 principal square root of 3 over 1 principal square root of 24. So we have two principal square roots being divided. So one of our properties says that, hey, you can write those as 1 principal square root. So this principal square root divided by this principal square root, you can write it as one big principal square root, and then it's 3/24. Now, why would I want to do that? Because 3/24 is really just 1/8. So I end up with 9 times the principal square root of 1/8. So basically, I got to simplify that fraction before I do anything else. It just makes my numbers easier to work with. So now I can go back and split them back apart. And now all my square root stuff will be a little bit easier. So the principal square root of 1 is 1. Principal square root of 1 is 1. Now all I have to simplify is the square root of 8. So that's what we've been practicing with. So let's see, top times top would be 9. Bottom times bottom would be square root of 8. And what we practiced earlier was how to just simplify a radical or a square root. So the square root of 8, we can simplify that. That would be 4 times 2. So that'd be principal square root of 4 times principal square root of 2. And the principal square root of 4 is 2. So now the bottom is simplified. But even though we simplified the square root of 8, the principal square root of 8, it still left a radical in the denominator. It left a radical in the denominator. So we got to get rid of it. So we're going to multiply by principal square root of 2 over principal square root of 2. We'll do top times top, and then bottom times bottom. And let's see what we get. We end up with 9 times the principal square root of 2. And we get 2 times 2 in the bottom. So our simplified fraction is 9 times the principal square root of 2 over 4. 9 times the principal square root of 2 over 4. So again, this number and this number represent the exact same value in the real number system. If I were to plot both of them on a number line, they'd be the same exact position. If I were to type them into a calculator to get a decimal approximation, they'd be the same decimal approximation. However, the one we got at the end is simplified. what else are we going to practice? Well, we're also going to practice how to just multiply radicals together, multiply principal square roots together. So um, for these next ones, we are going to multiply and then simplify. So this is just merely practice with our properties. So let's say I had 3 times the principal square root of 2 times 4 times the principal square root of 18. So what we're practicing here is how to multiply two principal square roots together. And then if we need to, we're going to simplify that. And often we will. There'll be some simplification we can do, but not always. Not always. So we're going in the way back machine. We're going to use the commutative property here. I'm going to rearrange these numbers. It's all multiplication. It's 3 times this times 4 times this. It's all multiplication. Multiply, multiply, multiply. So back in first semester, we said, hey, if you have a list of multiplication, you can commute your factors and reorder the multiplication. So I want to reorder this into 3 times 4 times principal square root of 2 times principal square root of 18. So that's our commutative property. That's not a new property. That's very beginning of the year. Now let's do our multiplication. This would be 12 times the principal square root of 36. Ooh, but we know what the principal square root of 36 is. It's 6. That's a perfect square. So this ends up being 72. It ends up being 72. And that wasn't obvious. It wasn't obvious when you look at this that it's the same thing as just 72. That's not obvious when you look at it. So you need to actually multiply those square roots together to see that, hey, look, that thing works out to just be 72. A regular old rational number, integer, whole number. Let's try another one. So let's say we had the principal square root of 8 times 7 minus the principal square root of 14. So all the properties we've been learning up to this point are still valid because these are all real numbers. So I'm allowed to use any property of real numbers I've studied previously, starting with the distributive property. We're allowed to distribute this. So I'm going to use the distributive property. Again, not a new property. This is the property we've used the most this year. Remember, earlier I said that this whole course could just be called a study of the distributive property, and that really is true. The distributive property is behind the majority of what we studied this year. So we go ahead and use the distributive property. Now let's see if we can clean any of this up. So um, 8 times 14, we can do that. And we get, let's see, 8 times 14 is what, 112 maybe? Okay, so we've done all our multiplication. All the multiplication is done. I don't think there's any other multiplication I could be doing. So now we want to simplify. So principal square root of 8, well, 4 goes in there. 4 is the biggest perfect square that goes into 8. And then 112, the biggest perfect square that goes into 112 is 16. So we're going to get 7 times principal square root of 4 times principal square root of 2 minus principal square root of 16 times principal square root of 7. So we're doing the simplifying part. So we're simplifying the square root of 8 and we're simplifying the principal square root of 112. So we get 7 times 2 times that radical minus 4 times that radical. And I think, yep, that should be it because principal square root of 2 and principal square root of 7, 2 and 7 are both prime. So those aren't going to simplify anymore. Let's go ahead and do one more just to remind us of something we haven't really dealt with a lot lately, and that is a mixed number. So if you have a mixed number, nothing has changed. We don't want mixed numbers. So immediately change it to an improper fraction. So as soon as you see this mixed number, change it to an improper fraction. We don't want the mixed number. Then just move forward like we've been doing. So this is a fraction one. And as soon as you split it up, you get a principal square root of 6 in the bottom. Well, we can't have a radical in the denominator, so let's get rid of it. And let's see, we're going to get 78, I think. And the bottom will just be 6. And then 78, there are no perfect squares that go into 78 besides positive 1. Besides positive 1, because 13 is prime and 6 breaks up into 2 and 3. So I think we're okay. So the main purpose of that example is just to say, hey, look, if you come across a mixed number, we don't want it. We do not want mixed numbers. So the moment you see one, change it to an improper fraction and apply any of the properties that you know can be applied.